But in terms of the first problem, you think back to the rules on the previous page. We didn't really talk about a quotient rule or a product rule or anything like that for integration. So this ain't that. And besides, there isn't something called a quotient rule or a product rule for integration. That's not a thing. All right, we have strategies that we use to handle quotients and products, but it's not as simple as differentiation where you just say, I'll apply the product rule or the quotient rule or the chain rule or the reversal. That's not how it plays out. So odds are you're looking at some algebraic process to get you through it. All right. So for this one, I'm just going to rewrite it. X to the negative fourth. All right. So now it's a power rule situation, the reverse of the power rule. So increase the exponent by 1. Divide by the new exponent. Right? The understood coefficient in front is a 1. So if I'm dividing that 1 by that new exponent, it would be 1 over negative 3. I choose to write that as negative 1/3. So negative 1/3 x to the negative third plus c. All right. Talked about this yesterday where you don't want to be the one person. The one person who forgets the plus c. There's always one. I'm hoping I'm not creating a self-fulfilling prophecy by saying that there's one person. I'm like creating the thing I'm hoping to avoid. Causality. 12 monkeys. So, I don't know. The TV show, not the movie. I didn't like the movie. From the 90s. Nobody knows what I'm talking about. That's fine. So, number 2, a little bit of a different story. Here you actually have to know some rules. Right? Not just the reverse of the power rule. It's not just algebraic. We have 4 distinct components. Right? You could, and I talked about this yesterday, I'll do it one more time and then this is the last time I'll do it. I'll write it as the 4 separate integrals. So this is the same as saying the integral or antiderivative of 3 to the x dx minus the antiderivative of e to the x dx minus the antiderivative of x cubed dx plus the antiderivative of x to the e dx. All right, this is something that we take for granted. It's intuition. You don't write this every time. And in fact, just how I'm saying this is the last time I'm going to write it out like this. Hopefully, this is the last time that you'll write it out like this. All right, you don't want to have to do it like this. You want to know that when you have a sum or difference contained within an integral, that you take the antiderivative of each part independently of one another. All right. So the first piece. Well, that's exponential function with a base other than e. So we learned that that's going to be 3 to the x over ln of 3. All right. And that directly comes from our knowledge of how to differentiate something like that. Because if I had to take the derivative of this, it would be 3 to the x times the ln of 3. So I'm just doing the opposite of that. All right. E to the x has an antiderivative of e to the x. I'm gonna write the plus c here. I'll put a little subscript there, show that that's the constant for that first integral. All right. Then minus e to the x, because antiderivative of e to the x is e to the x, and that also gets a constant, which I'll say is c2. Then antiderivative of x to the third, increase the exponent by 1. Divide by the new exponent. I just choose to write that as 1/4. Geez Louise. That part was right. It's this part that was the point. I said increase the exponent by 1, but it never did it. Classic Bob. That's not my name, though. TV show reference. If anybody knows that one, I'll be shocked.
You don't have to put 1 over 4. You could just put x to the 4th over 4.
Yeah. All right. So then x to the e. Now, don't get fooled by that. It's not designed to be a trick question. That doesn't mean it doesn't trick people. It's the reverse of the power rule. X to the e plus 1. Yeah, so 1 over e plus 1, x to the e plus 1. and then plus, I'll make this my fourth C. All right, so now we would never leave it like this because we know that, let me get this to a different color. I have to go to the palette, I think, here. Oh, that's a nice looking one. Okay. So this constant plus this constant plus this constant plus the last remaining constant would all amount, constant plus infinitely many constants, doesn't matter. It's still a constant, right? So we'd be looking at 3 to the x over ln of 3, which I'm going to write actually as 1 for consistency, 1 over ln of 3, 3 times 3 to the x, minus e to the x, minus 1/4 x to the 4th, plus 1 over e plus 1, x to the e plus 1, all plus a single c. All right. Again, I just did this in gory detail, basically. It's like, would I ever do this on a test? Of course not. Honestly, the only thing, and this isn't like showing off, because this is really the second example. I mean, we did some examples yesterday, but if you follow the progression of the packet, the first page was all rules. This is really the second example. It's not supposed to be difficult, all right? So understand that when I say that if I were doing this problem on a test, the only thing I'm writing down is the final answer. So you don't write down anything in between. All that stuff's happening up here in your head. The final answer is going down on paper. All right? This is all just for instructional purposes. And for the most part, if you ever see me kind of going off the beaten path with a solution to a problem, it's so that you understand the underlying theory. When it comes time to take a test, you don't have to demonstrate in all cases. Sometimes you do, but in all cases, no. You don't have to demonstrate the underlying theory, why things work the way they do. You don't have to invent calculus on a test, right? But everything's a lot easier if you understand the inner workings, right? You make the attempt, right? So that's why we do this. So, because I'm just kind of staving off the, could we have done it this way? Of course you could. You got the same answer? Of course, what do I care? All right? Short of cheating, it all works.
What rule did you use to go from HC to next step?
The reverse of the power rule.
Okay.
Yeah, because that E is still a number. It's just weird. A weird looking number. All right. I don't deal with it as much in the college, but in high school I always get, well, my tutor showed me to do it this way. And I'm like, well, that's cool. But your tutor is paid to show you the shortcuts to help you get the right answer. I'm paid to show you the inner workings, why things work the way they do. All right? And honestly, but there's no reason why you can't at least attempt to make the underlying connections. With that being said, later on this evening, I'm going to introduce you to the first technology assignment. Right? It's related to online software. I don't even know if they call it, when it's online, do they call it software? I don't know. Called GeoGebra. Some of you have heard of it, some of you haven't. Sometimes it's a real pain to work with, but the activity that I developed is not. Right? So, but it's going to give you a really good, I got good feedback over this, so unless all the people were just lying to me, I think it's true. It's going to give you a real good understanding of what on earth an antiderivative is really telling us. All right? Because we find derivatives, we find antiderivatives, but we don't always make the connection on, okay, what the hell is this thing? All right, what are these things? And that's really where we're at. But you get to number 3 and you say, okay, cool, you talked for the last 5 minutes about motivational things, but isn't this just a rule? Yeah. 5 sine x plus c. Gave you a lot of space for that one, just in case. That's my excuse for everything, just in case. Just in case what? I don't know. I didn't really think of that. I didn't think that far ahead. No, I'll take it. I'll take it as a typo. Yeah, that space is there so that it's consistent with number 4, like in terms of the amount of space, but I don't know, maybe, here's the typo, I think. Switch number 2 and number 3, right?
Yeah.
Because space-wise, those are more consistent. These are things that I only think about once I start going through it for the freaking 50th time. They say that when you start teaching a course, it takes 5 years before you really become proficient in teaching that course. So I'm on year 20, like I said, and I still have a lot to learn. Number 4, find the general solution for the differential equation. Probably need a "the" in there. Find the general solution for the differential equation. That's one for someone. dr d theta is equal to pi. All right, you look at that and you say, well, there's no x's and y's there. What are we going to do? We'll do the same thing we would do if there were x's and y's there. This is a derivative of a polar function, or a polar equation. So you're not going to learn about this till the beginning of Calc 3. Well, depends on where you go after this. Maybe some other class you take will do it. Maybe your Calc 1 class did it, but it's not typically part of the Calc 1, Calc 2 curriculum. All right. So we think of the r as a y. We think of the theta as an x. All right. So I'm going to do the same thing I would do if that were the case. So dr is equal to pi d theta. So that's the differential form. All right. What that gives us is a relationship between the instantaneous changes. All right. It tells us that the instantaneous change in theta is proportional to the instantaneous change in radius. All right, angle and radius in the polar function. That's something that's from pre-calc, so maybe you remember some of that. But that goes hand in hand with x's and y's. Whenever you have something that's in differential form, it's establishing a proportional relationship, which allows for predictability. You know, when something's proportional, it takes the form of y equals kx. All right, so an example of that would be like y equals 2x. All that's telling you is that all you need is some multiplier by one variable and you get the other. It establishes a relationship. If that relationship has cause and effect, now you have causality, and then from there you can draw lots and lots of conclusions. You can extend it to the real world. All right. So here at this point, we have the assumed 1 in front of the r. Integrate. Antiderivative of 1 would normally be x, but the variable here is r. So antiderivative of pi would be what? Pi normally x, but this time theta, plus c. All right. Now, I'm going to just kind of do a quick aside here. Or you might have thought it was r plus c1 equals pi theta plus c2. But ultimately, when I solve for r, I have a constant plus a constant. C1, C2, C30, it doesn't matter. Constant plus, constant minus, constant times, constant 2, another constant. It's all going to be a constant. So either way, you still get what you're looking for. All right. So actually, that gives us a polar equation that seems to be in the form of a linear function. It's really kind of an interesting to think about. When we kick into the graphing calculator, I'll show you what that looks like. It's kind of interesting. A little teaser of Calc 3.
Does it, on the right side of the equal sign, does it become pi theta? Because, I forget the name of the rule, but like, if you were to move the pi onto the left side of the integrand, would it just be the integral d theta?
Yeah, exactly. And also, anytime you have a constant, you could think of it as kind of like a hidden reverse power rule situation, because pi could also be thought of as pi theta to the 0th power. Follow the same process. Increase the exponent by 1, divide by the new exponent. You're going to get the same thing. You're going to get pi theta. All right. The 1 could be thought of as 1r to the 0th power. increase the 0 to a 1, divide by the new exponent, you're going to get an R. All right, so it's the power rule still at work. It's just kind of in a not really overly expected sort of way. All right, the first one where you might have got jammed up if you were going to get jammed up. All right, I have a strategy that I encourage people to use. I don't know if I've ever come up with a good phrasing for it, but I always say the same thing. It seems to work. Whenever you're trying to problem solve, work from the beginning of the course to the end of the course. And what I mean by that is don't go looking for the most complicated way to attack a problem. Look for the simplest way, all right? So you look at this, you see a quotient. You're like, oh, it must be something fancy, a reverse of the quotient rule. Or, I mean, if you've taken this course before, which is a possibility, you might be thinking, oh, maybe it's partial fractions or integration by parts or a trig substitution. It's like, this is a terrible problem. Why would he put this on the first little practice set? Beginning of the course to the end of the course. Think power rule, reverse power rule. Think some sort of generalized rule like a trig rule. In this case, that wouldn't make sense. And then you start graduating to the more complicated things like use substitution and so on. All right? So if I want this to be power rule, then I got to do a little algebra. All right, that's me saying split the fraction. It seems to work for the freshmen. High school freshmen, that is. Actually, who am I kidding? I think they like it even less than you do.
Can't you just get the integral of x to the negative 4 and then multiply the numerator?
Yeah.
Okay.
So keep the base, subtract the exponents. X to the negative second plus 2x to the negative third plus 3x to the negative fourth dx. And then, like I said in number 2, when you're dealing with a sum or difference, you don't have to break it up into separate integrals. And in fact, I said that was the last time I was going to do that. And here's me following through on that. For the first one, increase the exponent by 1, becomes x to the negative first. Divide by the new exponent. Coefficient, understood coefficient is 1. If I divide it by a negative 1, it becomes a negative 1. You obviously don't have to write the negative 1. You can just write the negative sign. But that's what it would become. All right. For the second one, increase the exponent by 1, x to the negative second. Divide the 2 by a negative 2, and you're getting a negative 1. For the last one, increase the exponent by 1, x to the negative third. Divide the 3 by a negative 3, you get a negative 1 plus c. All right, you can clean it up if you want. I've never lost sleep over that kind of thing.
I think it's supposed to be a minus 3x to the negative 4.
Ah, look at that. Thank you. Oh, now I'm locked out of erasing. All right, hold on. Got to get my white out. There we are. All right, so then that's positive. Yeah, positive, right? There we go. Thank you. Quality control. '21st century. Like hell on earth. So, parentheses aside, it's still the sum of two expressions. So, increase the exponent by 1, so 1/3 x cubed. Then you just need to know a fact. The antiderivative of secant squared is tangent tan x plus c. All right, number 7. Same story, different chapter. Somebody already got the little double radicals. So if you're thinking about that, find a different typo. And again, folks, if you submit a typo, wait 24 hours and then check Blackboard. If you didn't get credit, it's not because I didn't see it. It's because somebody beat you to it. All right? Because you got to understand, I point out these typos, your competition is all around you. You see? What's that? On Remind? Just page number, what the problem is. And if it's obvious how to fix it, then that's cool. You don't have to say anything more. But if it's not, then just tell me how to fix it. So, the square root of x, because this is not like the square root of the square root of x. That would be like the weirdest trick question ever. I don't even know if it's a trick question. X to the 1/2 plus 1/2. Yeah, it would be x to the 1/4, but it's like it doesn't bring anything to the party, It's like that's one where if that were a trick question on a test, you would lose all respect for the teacher, because you'd be like, "This is your idea of a trick question. You must think so little of us." Increase the exponent by 1 becomes x to the 3/2. Divide by the new exponent. You divide 1 by 3/2. That's the same as multiplying by 2/3. So that's the first piece. Second piece, second piece, increase the exponent by 1. It becomes x to the 1/2. Divide by the new exponent. 1/2 by 1/2 is just a 1, so I'm just going to put a little plus sign there. Plus c. And boom shakalaka, as they say. Now, number 8, it's not a trick question now, but it will be sometime late next week, because you'll see other problems that kind of look like that, and it'll involve inverse trig integrals. You'll be like, oh, okay, so clearly I have to draw a triangle and develop a U and A substitution, whatever that means. You won't know for a little over a week. But you'll kind of start to neglect all the early stuff. That's why I'll repeatedly say this: work from the beginning of the course to the end. All right? Because sometimes I mix in problems where it's there to remind you that the simplest approach is often the correct approach. All right? So for that one, distribute it out. If it was raised to the 13th power, yeah, don't distribute it out. Look for some other approach. But to the second power, it's FOIL. -4. Of course, I do that, right? And like, I emphasize something and then I screw it up immediately. That's like my MO. All right, so 4t to the 4th minus 4t squared plus 1 dt. Notation is very important, not always for me, but sometimes for you, because I can't tell you how many times I've seen this very thing happen. A student will distribute that out, bless you, and forget to write the integral symbol. And because they forgot to write the integral symbol, they forgot to integrate. So they took a Calc 2 problem, an early Calc 2 problem, and made it an early college algebra problem, where it was just distributing it out. And they would just leave it at that. And I'd see a little check mark next to the problem. And I kind of imagine in my mind, wow, this person must have felt so satisfied. Haha, I didn't fall for your trick. I knew exactly what I was supposed to do. They forgot the part where they're supposed to integrate. And so there really was no trick. It was just the definition of tripping at a finish line. All right, so just be careful about little things like that. Like when I harp on notation, it's because the notation tells you to do something. It's a recipe. All right. Some people are just mean-spirited. They harp on notation because they want to have points to take off. Sometimes I'm like that too. But for the most part, it's so that you remember what your goal is at all times. You know, remember with limits, I'm sure there's at least a couple of people in this room that when you're finding the limit of a function, you did some algebraic manipulation, but you lost a limit along the way. And you just did the algebra. And then eventually you applied the limit, but you didn't write limit every step of the way. And you lost some credit for that. And you were not thrilled because you thought it was overly nitpicky. The teacher's vantage point is that they don't know that you knew why you were doing what you were doing. If you write the limit every step of the way, it's obvious that you know that at some point, yeah, you're doing all this algebra, but you do have to apply that limit. And so when you eventually plug in the number, that limiting constant, they know that you know why you were supposed to do that. All right? It's a little mixture of, you know, assessment, but it's also making sure that you're always paying attention to the details that make all this stuff work to begin with. All right? And that's the same idea with the integration symbol. So don't lose the notation. Can't emphasize it enough.